we are about to address basically a new topic. And I will, as in previous times, I will recap what we've talked about previously before we go ahead and define the new topic. And the idea is that what we're dealing with is what we refer to as non-conservative transport, as opposed to conservative transport, which is what you've talked about. And of course, it's not in a political sense that we're talking about that. We're talking about conservation of mass of solute within the flowing material. So let's maybe go through and talk about just summarizing where we are so far. And so we'll make the point that so far we've talked about conservative transport. Oops. Stop it, please. Okay. So the basic idea is that in weeks 2 to 2.1 to 2.7, we talked about this, right? Multi-phase flow, interfacial phenomena are important. They hold the stuff where it gets to. The rate at which it can move in the subsurface is controlled by relative permeabilities. The locations where it gets to are controlled by capillary pressures and their distribution in the subsurface. But ultimately, we end up with some system that looks like this, and this is our source. So it's basically a source. And this source is for dissolution. And so depending on the distribution of these saturations, which we'd expect to be quite small in this chimney, maybe, is that a mouse? Maybe 20% NAPL is left there as an irreducible smear as it goes down. And maybe it's close to 80% in these lenses. And the idea is that once it gets into place in the subsurface, and you've looked at this figure multiple times, is that you can look at the loading this provides in terms of time versus relative concentration. And that loading might look like, I don't know, something like this. And if you look at the behavior along a core, then it might look something in terms of spatial distribution. So this is X along the core, and again, relative concentration. And the final one would be the RTD curve, residence time distribution curve. Again, concentration over initial concentration, and this is time. And painting it with a very broad brush, we can say that the concentration distribution we could think of it as looking a bit like this. And we know now that this isn't quite true, but if we look at, so this is the source region that's coming from this, it's turned on at time t0. And that if we look at this time it takes, or the length it takes, it can go downstream, we can just get that from velocity is equal to length over time. And we can rearrange this for length, and we get that this length is equal to the product of advective velocity and time, roughly. We know that's not absolutely true. And if we look at the RTD curve, then we expect this breakthrough to occur like this. And this would be a time, if this is at time t0, that we put the stuff in here. So all of a sudden we turn it on at time 0. It was 0 concentration, and now it's all of a sudden a relative concentration of 1. I guess this is 1s, and this is 1. Then the time that it takes to get here is just going to be equal to the length traveled divided by the advective velocity, just by basically rearranging this expression here. And so this physically represents that the curve, the stuff going downstream has flown this far, has traveled this far. We know that that is not completely true because even if we give this step function behavior, we know that if it's dispersive, then it'll be kind of a muddled front, because there'll be some fast pathways and some slow pathways that will allow this fingering to occur. And that means that if you look at the arc residence time distribution, it's also distributed around this behavior here. So in other words, you get some early arrivals from these parts here. You get some late arrivals because these parts here have to work their way through the system. And I suppose this here would be this particular length that's used here, right, to get out the other side. And we know that we can represent this by a straightforward relationship, and that is that we can look at change in concentration with time, and that's equal to some coefficient, which we'll call dispersion coefficient, times d2c dx squared minus the advective flow multiplied by this. And it's not particularly important to understand exactly how to solve that equation, but it's perhaps useful to be able to define what these individual terms are. This is accumulation. This we could think of as a bucket, which I'll draw as a bucket, which is mass rate in, mass of the dissolved solute, in other words, not the water, but the dissolved solute is being carried by the water, whoops, versus mass rate out. And so that's this term here, or both of these terms here actually, these two. But this is due to dispersion plus diffusion, molecular diffusion. And this final term is advection. And so we also know that this dispersion diffusion term here, if I draw it down here, is equal to two components. It's equal to diffusion, which is molecular diffusion, the idea of dropping a drop of ink in a beaker full of milk. Slowly it spreads out by molecular diffusion. It's not being carried by anything, but it's trying to get rid of, by Fick's law, this imbalance between a big concentration gradient of ink in the middle and trying to get rid of that concentration gradient by spreading it out until all of the milk becomes light blue if it's a blue ink. And plus a component which is this dispersion, which is this dispersion coefficient multiplied by an advective velocity in the x direction or whatever. So this is diffusion, this part here, and this part here is dispersion. In other words, mechanical mixing. We had this figure of grains of quartz with fluid going through it. It chooses these tortuous flow paths, and so instead of being a Manhattan-style skyscraper with a kind of a box distribution, it goes downstream and it becomes this Gaussian distribution, like the grade point curve, right? A normal probability distribution function. And so that's what we've dealt with so far. And so everything we've talked about has been in terms of what we'll refer to as conservative transport. And so we've used this to be able to say something about some different things. So I guess in the first class, so this has been 3 1, 2, 3, 3. So 3, 1 was defining this equation and what it means, mass in, mass out, accumulation versus, so what goes in and doesn't come out, net accumulates. That's really what this conservation of mass law is. And it can go in carried by advection, or it can go in by diffusing into the system. Those are the two mechanisms by which it can go in and come out. And if there's more goes in than comes out, it net accumulates. If more goes out than goes in, then it net depletes. And so that's what this term is on the left-hand side. Just a physical statement of these, of what a differential equation is. We know that when this dispersion coefficient is equal to 0, then we kind of expect it to be this sharp front that occurs. And we know that when this dispersion coefficient is greater than 0, then it will not be this boxcar distribution anymore. And we also know that as it gets larger and larger, then it'll get flatter and flatter. So that's kind of the behavior, because it gets more diffuse. The other thing which I think is important to know, which is from 3.2, is that this really, although I've written this again here, this really isn't quite true. Sometimes it's offset from here. And it's offset from here because this is just a simplification of what's going on. And for instance, one way to prove that to yourself is to imagine that if the advective velocity is 0, then if the advective velocity is 0, then the length this goes at any particular time has to be 0 from this axis. And if it's only going 0 from this axis, that's not reality, because we know that even for something with no advective velocity would kind of diffuse downstream. And so this can't be true. And so we know the conditions for that are, maybe the conditions for that not being true are for Peclet numbers, which we defined as a velocity, a length, and a dispersion coefficient. For Peclet numbers less than 1, or maybe less than 10, this is not true. If they're 10 or greater, then this is a pretty good approximation of what's going on. And we can always, if we know the advective velocity and the length that it's traveling, and calculate the dispersion coefficient from this parameter here, which is typically equal to the length divided by 10, which is kind of strange. It doesn't have any material properties in it. It's just the length of how the plume's traveled. And we rationalize the fact that this term is only a function of how big the plume is, with the idea that a small plume doesn't have a chance to see lots of really fast conductors, but as the plume gets larger, then it has a chance to be able to see these big stringers that allow it to go very quickly. And as it gets even larger, then it can see stringers and faults which are even larger and allow it to travel even faster ahead of itself. So it's strange that this term here is not a function of any material property like permeability or porosity, just a function of the length of this plume. But that's the way it is. And so if we know the values of all of these terms, we can calculate Peclet number, and we can see whether this is a good approximation. And if not, then we can use the stuff that we talked about in week 3.2 to be able to calculate that, just by solutions of this equation. So that's where we are. And so now, what we'd like to be able to do, and I guess in 3.3 you talked about different geometries, planar geometry, this cloud-like geometry going downstream, and being able to run experiments in the laboratory to be able to figure out exactly what this term is. And the conclusion is that if you're in the laboratory trying to measure this term, because you have to apply just a very big velocity to the system to get fluid through the system to get a solution, laboratory experiments aren't very good. But field experiments, where you look at how the plume grows by taking snapshots at maybe a variety of different times, allows you to be able to come out with a field estimated value of this dispersion coefficient, which you can then use in forward models of this to look at where the plume might be in another year or 10 years if you do nothing, and to be able to design a remediation plan to be able to do something about that. So that was kind of what we dealt with in those 3 classes. And so now everything for those was what we refer to as conservative transport. Everything that gets dissolved from this upstream zone and gets put into the flow tube remains within the water all the time until it comes out at the other end. But for some of these components that get transferred downstream, there's an opportunity for them to sorb onto the grains. And if that material sorbs onto the grains and is stuck on the grains and removed effectively from the flowing water, then you're depleting the amount of mass within the system. So no longer are you conserving mass within the water because you're attaching some of it onto the solids. And so what we'll talk about today is what happens if you look at non-conservative systems. And so that's our idea for today. So non-conservative. And so the idea here, and it's especially true for these dissolved solvents, typically they don't attach themselves to quartz grains in sands, but if there is any organic carbon, in the same way that you can imagine putting these solvents dissolved in water through an activated carbon filter to take that out into the carbon, that is exactly the same process that will act in an aquifer that has not activated, but natural carbon sitting in it. And so that's the mechanism by which it gets removed. And so what we could do is we could take this equation and we can add a few extra terms. And I will write these terms as this. And so this extra term, which we'll come back to, represents, why does it keep on doing that? It must hit something bizarre that allows it to do that. Is that this term allows retardation to occur. And so just to define the terms, D is equal to the bulk density of the aquifer. And it's commonly, for sands, would be a bit less, but something like 2,000 kilograms per cubic meter, ballparkish. Theta is equal to the volumetric moisture content, when we talked about unsaturated flows. And operationally, it's greater than, well, it could be 0, I guess, greater than or equal to 0, and less than or equal to porosity, which we've called N. So this is just the maximum value, if it's fully saturated, is going to be equal to the porosity. And this behavior mimics the amount of material. This is kind of the rate of removal from the liquid, and C star is the concentration on the solid. Of solute sorbed to the solid. Solid being the grains in the aquifer. And so the idea is this. And let me do one manipulation first. And this manipulation is back on this expression. So the point is here that we solve for concentration in the water, C, not C star. And so we want to be able to solve an equation that only has C in it and doesn't have the effects of C star. So what we could do is we could multiply this by 1 by just writing this. And if we do that, then you see that if we gather these two terms together, then we have a term that represents the rate of change of concentration on the solid as a function of the change in concentration on the liquid. And I suppose I could rewrite this. Why don't I just rewrite this? So it's minus bulk density on the solid, volumetric moisture content, and I'm going to write this as dC star dC, the term above it, and change in concentration with time. So if you like, this term, which is black here, is the other term, right? So all I've done is switch them over, just as a convenience. So now, if this goes back into this equation, it's all written in concentration, all in concentration of water. And so if we can figure out exactly what this term here is, then we can put that in as a material coefficient. And so it's pretty straightforward to figure out what that is. It's actually an isotherm, which you will have seen in other classes. So the idea is this. If I draw a little figure. So in other words, you take a beaker and you fill that beaker up with your aquifer, and you put in some fluid that has some concentration in the water, and you solve it. And so you measure the concentration that develops on the solid as a result of you putting this concentration in here. And so the easiest way to kind of think about that is that you do this experiment and you plot the data. And so if you can imagine with time, you could plot, for instance, the concentration C star, which is on the solid. And so you add some stuff in at concentration 1, and you see that over time, this changes the concentration on the solid by some amount. So this is at concentration 1. So that by the time you get to some, over some, well, let me do a different color. After you get past some time here, then it's basically a constant. Then you go back and you put in a second concentration. Maybe C2 is equal to 2 times C1. And if that's the case, then you expect the concentration to go up to, you get the picture, it's roughly double the amount. And then it goes over time. And this becomes this. So this means that you have to measure what the concentration of the solid is as a function of C2 is equal to 2C1. And then what you can do with that information is you can just plot now, again, this concentration on the solid, C star, which you have these curves. Oops. And you plot it against the concentration in the water. And so this would be C1, this would be C2, and the two data points that you end up having are these two here, right? This is the equilibrium concentration you have for twice the concentration, equilibrium concentration you get for half of a single, and you end up with a curve. And this curve has components which are C star and C1, or C rather. And if we come back to this term up here, that's exactly the two components we have. And so we're actually going to call this a distribution coefficient, K sub D, and we're going to put this equal to 1. Right? So in other words, just by definition, we're going to take these two components, dc, dc, and we're going to define a term which is called the distribution coefficient, and I'll write it out. So Kd is the distribution coefficient. And I suppose it's defining the distribution of that material between the water and the solid, how it's partitioned. It's partition coefficient, in other words. And so the idea is that we can measure this parameter and calculate what it is just by doing this very simple experiment. And if we've done that, then we can now rewrite this top expression to accommodate that. So I'm going to make it smaller so I can put it on at the same time. So if I write this expression at the top, so accumulation term is dc dt is equal to this dispersion term d2c dx squared minus advective velocity times concentration with length minus now this term. It's going to be density divided by volumetric moisture content. I'm going to put the part which is in the red here, which is in the green here, together, which is going to be Kd over 1 for this, and multiplied by change in concentration with time. And so the idea of doing that is now this term here and this term here are the same. And so I can now just rewrite that as rate of change of concentration with time is equal to 1, which is this term, plus this term here. And bulk distribution coefficient, and is equal just to the regular right-hand side. Minus velocity, advective velocity, dc dx. And we will call this a retardation coefficient. So this is just a term. This is referred to as uppercase R, which is called the retardation coefficient. In other words, how much as you'll see in a moment, how much the concentration is retarded, delayed in arriving, and also how it's attenuated somewhat. And so if we write this expression out as change in concentration with time times retardation, the dispersive part, diffusion and dispersive part, I don't want to belabor these equations because it's just what these equations mean that's important to us. So now, if you look at this, I guess I can't go up quite, there's probably, hopefully that's big enough on there. So you see now, this term here looks just like the first part we had to the left-hand side of this line before we added this extra term. It's just that instead of this being 1, it's now equal to R. And because this number is always going to be bigger than 0, R is always greater than 1. That's the range of this. And so the utility of us doing this is that now we can use everything that we've tried to understand before. I guess it won't get smaller than that. In terms of understanding this equation in terms of the source, what the plume looks like in the core, or the aquifer as it goes downstream, and what the residence time distribution looks like as it comes out at the bottom of this. We did that only where this part here on the right-hand side didn't exist. Now we've kind of made this part go away because we've taken it onto the left-hand side of this equation. So what we're probably going, well, not probably what we're going to do, but exactly what we'd want to do is we can do this. So we can divide both sides of this equation through by R. And now we have an expression that is this times 1, exactly as we had before, right? We made this point that this is just 1. And it has these modified coefficients. Instead of being just the dispersion magnitude, it's the dispersion magnitude divided by this retardation magnitude. And instead of just having advective velocity, it's advective velocity divided through by this coefficient. And so now you can imagine that these coefficients, modified coefficients, allow us to use all the equations and solutions to the equations that we looked at in 3.2 a week ago today, I guess. They get to be complicated exponential terms and error function terms, but allows us to be able to look at what the plume would look like in reality. But we can also, just from looking at these individual components and what they mean, we could guess exactly what the behavior would be that we'd get out of this. And so we can draw it again. Am I going to capture that? No, it's going to get too busy. So I'm going to do exactly the same as we have at the top. So we'll look at the source term, which is concentration with time that gets turned on. Look at the concentration as it goes downstream within the core. And look at the residence time distribution that we get out at the other end. And so what do we think that will look like? So we said before that this might look like this, where this is equal to length is equal to velocity times time, advective velocity. So, but now, in this modified case, we're dealing with an advective velocity which is divided through by retardation. So retardation has to be greater than or equal to 1, and I guess less than infinity. So typically it might be of the order of 1 to 20, depending on what the material is. And so since this operates on velocity, we could do the same calculation, and this length traveled would be equal to the advective velocity divided through by retardation multiplied by the time it's taken to go from being put into the aquifer and go downstream. And so physically what that means is, since r is always going to be larger than 1, it will have gone less far. So it means that physically the plume in this particular case might have gone only this far in the same amount of time. So it means the definition of retardation is it's retarded. It can't go, it's delayed in going downstream. And so that means that if we look at the residence time distribution, which before we could we know that this isn't absolutely correct, but before we could write this length as being, or time being equal to length over velocity, right? So length, well, length is meters and velocity is meters per second. So by definition, that's time, just from the units. And because this is velocity that's in here, the time, just by substituting, instead of v, you substitute v over r, then this would be equal to length times retardation divided by the true advective velocity. Right? And so the time at which breakthrough occurs, instead of being at the point there, it'll be somewhere over here. Right? It's going to be delayed. Because it's going slower, by definition, you'd expect it to take longer to get there, to come to the downstream portion, and so it'll be delayed. And so we can think of these merely in a functional way, that retardation slows it going downstream, and so it will go less far in a given time, and it will therefore take longer to arrive a given length down the aquifer. And that's really what it is. So that's the first part of it. The second part was that when we looked at these individual figures up here, we said that we get a very sharp front if there's no dispersion. In other words, if dl is equal to, dispersion coefficient is equal to 0. And as it becomes larger than 0, progressively, maybe the midpoint will still be the same part, but there'll be a fast arrival because of these fingers that arrive faster. And there'll also be a lag by the backs of these fingers that have been delayed because they're going through much less permeable material. And so we'd expect to get this general behavior where it canters over. And so a small magnitude of dispersion coefficient gives us a very sharp front. So if we are dividing the true dispersion coefficient by a number bigger than 1, it's going to be smaller. And so effectively it means that it would sharpen the front. So in other words, not only would it take longer to get downstream, but the front as it goes through would tend to be sharper. And so maybe I should go just below this and draw two cases out that kind of mirror this. So in other words, actually I can do it on here. I won't do that. And so I'm going to do that in a different color. So in other words, this is for dl equals 0. If dl was greater than 1, if I can, or greater than 0, so this is dl greater than 0. And so what happens if it was in the same medium, same material that it's flowing through at the same velocities? What would this front look like? Would it look like being more canted over than this one, or would it be sharper? Presumably that if we do the same thing for this one, then the green here is for these two cases are the same. But if it's for the case where dispersion is occurring, then I suppose we'd expect this to be actually sharper. Whoops, not doing very well. Shouldn't go behind there. See if I can do a better job on drawing it. The only important thing is that it should be, if you like, sharper than this. This one here is quite flat, canted over. This one here should be almost vertical. And so both of these are a consequence of these two terms. This term means that the advective term carrying it downstream means it doesn't go quite as far in a given amount of time because it's delayed by this coefficient, which is greater than 1. And so the consequence of this for a residence time distribution is that it would also arrive at a given length later if it's retarded than if it's not. Difference between the green and the black. And the second term is that this physical term references how steep the front will be. If this term is equal to a very small number, 0 in the limit, then it will be plug flow will be vertical, and as this term gets larger, it'll be flattened out. But in the case for the retarded flow, because this number is greater than 1, then the front will, it's called self-sharpening. It will become sharper as a function just of the fact due to retardation. And so that's basically our discussion, if you like, of retarded behavior. So hopefully that makes some sense. The reality is also that it's not so obvious with this. You could also imagine, and it doesn't really come out of the math that we've talked about here, you could also imagine that this residence time distribution might also look like, let me try and draw it separately. So you could imagine that the residence time distribution might look like this. And so instead of being at a relative concentration of 1, which is what these ones are, right? If it goes in at 1, it comes out at 1 because it's conserved. You're taking some of that mass that was in the fluid and you're attaching it to a static grain that's not going anywhere. You're only measuring the concentration in the fluids that goes downstream. So this would represent the amount here that has been removed and to put on the solid. I can probably do it better. So this amount here we could think of being removed to solid. And this amount here would be the amount that's still in the water. So I suppose in our terminology, this would be C, and this would be C star, right? This removed. So that's about as physical an explanation of this that I can muster. So you'd expect to see these two things. One is it is retarded, delayed, so it goes less far in a given time, and to go a given length to come out of the end of the aquifer, it takes longer to get there, which is embodied in both of these plots here. And because it responds to this reduction of this dispersion, the effective dispersion is reduced, and so it becomes sharper if it's retarded. And so you'd also expect that the breakthrough curves, although it was delayed, it would become sharper as well. And not included in this equation, but what makes, I hope, eminent sense is that if you're removing some to put it on the solid and it's taken out of the flowing fluid, there's less mass in the fluid, and so you'd expect the downstream concentrations to be less, attenuated. So hence our choice of this behavior to represent retardation and attenuation. So retardation means it gets there later. Attenuation means when it gets there, it's in a lower concentration than it would have been when it started out. Okay? So that's probably the best way to introduce that, just by drawing it out, and return to the notes now. And so, yeah, to make the point that we just talked about, these two cases, getting there later and getting there at a concentration which is less. And so that's what that means. And so we've gone through a bunch of stuff. Don't need to do that, so because we've just done it. We talked about isotherms, and in your other classes, no doubt, you'll also talk about isotherms. This is what the distribution coefficient is. This figure on the top is exactly what we talked about, that we can get by doing this very simple experiment that takes, if I can never find this. So this very simple experiment where we put stuff in contact with the aquifer and we measure the concentration on the solid relative to the liquid aqueous concentration, and we plot those against each other, we get a linear relationship. Sometimes that relationship is not linear, and if it's not linear, there are a variety of different isotherms that describe that behavior. Two very famous ones are the Freundlich isotherm, which is just a power law relationship relative to concentration. If n is equal to 1, it's just exactly the distribution coefficient, the linear equation that we talked about. If n is greater or smaller than 1, it just gives different concavities to that relationship. We won't use either of those. We won't use that. And also a very commonly used one, the so-called Langmuir isotherm. And the Langmuir isotherm basically says that there's only a finite number of sites where those sorbed molecules can sit. So you take it out of the solution and you put it on a surface, then that allows you to go up this, as you increase the concentration in the water, it allows you to go up to some location. But once you fill up all the sites, it can't take any more. And so it has a finite capacity on the surface to be able to accept new sorbed material. And that's also a very common behavior that you see. But if you're only working at very dilute concentrations, which is typically what we are, you're only working on this very first part of the curve, and so you never get up here. And so for that reason, our systems will always assume that they're linear. That's tough enough for us to do, and we'll deal with it that way. This again is exactly what we've talked about. This figure at the base tries to make exactly the point that I've been drawing, and that is that if you think of the distribution of the fronts within a core or within an aquifer, as you feed it in from the upstream location to go downstream, if you look at the case where you don't have sorption, in other words, it's conservative, unretarded, I guess, by definition here, is it might look like this. It would have traveled this far, and the dispersion would have made the curve look like this. But if that particular solute is being sorbed onto the grains that it goes past, in the same aquifer, moving at the same advective velocity of water in the system, then the plume for the retarded, the non-conservative part, would look like this. Two important features. One is that it would be delayed relative to the conservative one. This is non-conservative, this is conservative. And second, the front would be sharpened for what we talked about, the fact that it would reduce the effective dispersion amount. So you see these two effects. So that's just reiterating that behavior. And so the bottom line for that is that you could use all of the equations that we talked about in 3.2 that take this advection dispersion equation, but instead of using dispersion coefficient and advective velocity, you just substitute into those equations the values for dispersion coefficient divided through by retardation and velocity divided through by retardation as well. A number. Still the same units. R is dimensionless. It's either 1 or bigger than 1. So if it's 2, then it's just reduced the dispersion by a factor of 2.5, right, from 2. All right, so we could talk about all this. We don't need to. I don't think that's necessary. So what does this look like if we look at it in the field? So this is an example from the same field site that you looked at in part 3, and that was this Borden, Canadian Forces base in Borden, which happens to be a nice shallow sand aquifer where you can dig a hole and you can put a nice cocktail of materials, TCE and PCE and salt that dissolve in water, and it is within a flow field and it gets carried down gradient. It's underlain by a clay bed, so it doesn't go into the underlying groundwater. And you can follow this plume by just taking capillary tubes, long, thin straws that you push into the ground, and you suck samples out to be able to get a picture of what the concentration distribution looks like around this cloud that's going down gradient. And so you did it last time for a chloride plume, and the chloride plume after 2 years had gone something like 57 meters downrange from the source. But in the same cocktail that was put in the ground, also carbon tetrachloride was put into it, and also perchloroethylene, 2 different components. And if you look at what those plumes look like from day 0 to 2 years, then these are the 2 different plumes. One has gone moderately far after 2 years, one has gone less far after 2 years. And so if you take the plumes as they look after 2 years, then the chloride's gone 57 meters downrange, the carbon tet has gone 23.5 meters downrange, and the PCE has only gone 13 meters. And so that's really a manifestation of exactly what we're talking about, that the distances traveled, this is a different boundary condition, right? This boundary condition is you turn it on and you keep it turned on for all time, and you get this linear distribution. If you turn it on once and then take it out of the ground, then the distribution you'd probably expect to get here would be something that looked like this. And for this, which I guess would look like this, right? Sharp and traveled less far, bless you, and quite shallow and traveled more far. And so this would be for a constant boundary condition, the red, and the green would be for an ephemeral boundary condition, right? So you'll remember that when we drew these figures, we could draw 2 different boundary conditions. I think we've got some space here, right? Is it here? No, that's from last year. This is this, right? So you realize that we could do the boundary condition as either it is here, or the boundary condition could have been this, in which case these would start looking like this, and this would also look like this as well, right? So this is the skyscraper boundary condition versus the heaviside function boundary condition. And so clearly for the Borden case, the boundary condition at the upstream is just this turn on and then turn off behavior. But you see that these have traveled 2 different distances in the given amount of time. And so what we could do is we could look at the advective velocity is equal to length over time. And we could look at the magnitudes of, I suppose, actually probably the easiest way to look at it would be to look at the Okay, so this is for the unretarded one. This is for the retarded one. Right. And so if we wanted to deal with this, so this is the length traveled by the conservative one here. And so what we could do, I suppose, is we could substitute this in for this expression here, in which case we'd end up with conservative length traveled over time times retardation is equal to length traveled for the retarded plume divided by the time taken for the retarded plume to travel. And if we look at this snapshot at the two same times, so these cross out, and I suppose if we just rewrite that, then hopefully this is right, then the retardation coefficient is going to be equal to the length traveled by the conservative plume divided by the length traveled by the non-conservative plume. And so the length traveled for conservative plume is always going to be 57 meters. And so we could calculate the retardation coefficient for T carbon tetrachloride, CTET, which is going to be 57 meters divided by 23.5. 2 times 23.5 is 47. So this is, I don't know, it's about probably about 2.5, right, of that order. You can do the math. And for the other system, so for PCE, it's also going to be 57 meters traveled divided through by 13 meters. 3 13s are 39, 4 13s would be 52, is that right? So this is about 4.2, not sure, of that order. Yeah, that's about right. And so what that allows us to do is get retardation magnitudes from this. So now, if you wanted to project where these plumes would be, various plumes would be in another 2 years, well, actually it's not very difficult to do. This plume would have traveled twice as far. It would have traveled 114 meters. This plume would have traveled 1 over 2.5 times this amount. Actually, they'll just scale directly with this. So it would be 27 meters, and 47 meters and 26 meters, because it's just being carried by the advective behavior. And the same things that we talked about last time was that you could use the magnitude of this length, the half length of the plume, you could use that to calculate the dispersion coefficient. I won't repeat that, but you can do that. So in other words, this will now represent dt over retardation, because we said it's modulated by that. In this case, retardation is equal to 1, because chloride is a conservative ion. It doesn't sorb onto the soil. This one, you could do the same by calculating this, but now the magnitude of this would be equal to 2.5. But you could still calculate it again just by taking the length from the centroid out to this length here. You could just take this length here, and I forget what the expression was, but the expression was something like 3 standard deviations is equal to, well, actually we can go up. Let me just zip back to that, because it was immediately before this. You were record this term here. In other words, this is the expression. So this term, this is the length that we have. This is what we called L. So 3 square root 2 times dispersion coefficient times time. So I'll try and remember that as I flip through back to here. See how smart I really am, or not. And so in other words, if we know that length is equal to 3 times square root 2 times dispersion coefficient times time, but this is retardation, then we can measure this length here, whatever that length is. We know that it's 2 years since we started going. We know that retardation is equal to 2.5. And so we can get dispersion that should come out of here. And this dispersion, I guess, should be the same as this amount here. It's because it's being corrected for the effects of retardation. You'd expect it to be the same. And so we can use the same rationale before. So that's important. So that we belabored maybe the fact that we have these diffusion, advection diffusion equation, and it looks slightly different. But the really important part to come out of that really is that this relationship that we have, I guess it was in one of these, is that we can always use that. We can always use this relationship here so long as we just use the modified coefficients. Don't need any other equations. We just need to modify. And actually you can always use these coefficients because if it's conservative, then R will just be equal to 1. And you'll get the original equation that we had, that we used previously. Okay? All right. Getting close to having said as much as I wanted to. I suppose the other thing that it might be worthwhile mentioning is that since from this field experiment we can get values for retardation, so we can get magnitudes of this, then if we wanted to, since we know this, we know this is 2,000 kilograms per cubic meter, and we could presumably measure the value of in situ moisture content, which if for saturated aquifer is equal to porosity, which might be 5% to 20%, something like that. So we have some numbers for this. So the only thing that we don't know is distribution coefficient. And so if you want to get distribution coefficient, instead of doing something in the lab by putting fluids that have some concentration of aqueous solvent in them, dissolved in water, and then calculating how much goes on the solid, you could use a field experiment, and we could rearrange this expression here to get the distribution coefficient. And so if you can measure this and get this and this, then you can get the distribution coefficient. And that's just what's being done here, is to work out exactly what this value of distribution coefficient is. And it has units of volume per unit mass, as you could work out from the equation, right? The units of this have to be unitless, and so the units of Kd, since theta is equal to, has no units, the units of Kd have to be the reciprocal of density. Density is mass per unit volume, so Kd has to be volume per unit mass. So the volume of solute dissolved per unit mass of the solid aquifer is basically what it is. And so we won't do anything with these values here today, but we will come back to this example and talk about the effects of sorption and try and calculate what the Kd values are by using some empirical relationships that define the behavior of organic solvents in attaching to organic carbon that is present in the aquifer. So that's the last thing that we'll do with that. So the final slide, I think it is for stuff today, is that sometimes sorption or processes that look like sorption aren't sorption. And it's kind of equivalent to the fact that we talked about diffusion. Diffusion means that the plume looks like it spreads out over time and it's driven by concentration gradients. But we made the case that when we're talking about flow downstream in a fractured medium, there are two effects. There's diffusion, which is molecular spreading by Fick's law, Brownian motion, and also this tortuous flow paths, which spread out the front from being a concentrated blob into something that's much wider. And so for flow within fractured rocks, this behavior that you get a retarded plume hasn't gone as far as it should have done in a given amount of time. And in this case, actually, it's not sharpened, it's maybe softened, can occur for other reasons. And so the other reasons here would be if you imagine a plume going down a fracture to get to some place, you'd have a very sharp front. No sorption occurs onto the material that's around it, and so everything that starts up at the upstream location ends up at downstream. And so you'd expect this kind of plug flow. If you allow the material to be porous, so that there is water in the pore space, then as it goes downstream, then stuff can diffuse into the water by molecular diffusion, and as a result of that, some of the mass will be lost here, and if some of the mass is lost as it goes downstream, you'd expect to have exactly the same behavior as if you have sorption. The mass that now goes into here can't arrive downstream, and so the front doesn't go as far in a given time, and so it's retarded in the distance it travels. And if you then imagine that the material that diffuses into this zone here then sorbs onto the grain surfaces once it's in there, then you lose mass by two mechanisms. One, it diffuses into the pore space and is held in the water, but it's lost to the main flow and so doesn't turn up here. The stuff that's in the water then goes onto the solid and is removed from that water, so the water can, by Fick's law, remove more by the concentration gradient into the pore space, and so you double lose the amount. And so this front now is doubly retarded over where it would come before. And so this behavior is not really sorption, it's by diffusion into the medium. This is by sorption, but not onto the fracture walls. There's much more there's much more surface area within the aquifer than there is compared to the relative small amount which is present on the fracture surface, and therefore it can potentially be a big effect. And that's it. And so we've made the case for the fact that we have non-conservative transport. We kind of summarized what the advection dispersion equation means if it's conservative. We added an extra term on the end that allows for stuff to be removed from the liquid part and put onto the solid. We can define that in terms of isotherms that we can call linear isotherms and a distribution coefficient, which is probably adequate for what we want to do. And then we can use that to be able to redefine our coefficients for dispersion as dispersion divided through by retardation, and advective velocity divided through by retardation coefficient. R is just a non-dimensional term that reduces each of those parameters, and we can use all of the tools that we've used so far to be able to predict how far it goes downstream, when it will arrive at some compliance point, and how much the concentration will change within the aquifer as a result of that, just by using those very simple concepts. So what we'll do next time is we'll try and figure out exactly how we can get the magnitudes of these distribution coefficients, KD, that we've talked about, and relate it directly to some chemical characteristics of the solutes. And those would be the solubility of these dissolved components, or the octanol water partition coefficients of these solvents, and be able to use that directly to be able to say what the distribution coefficient is that is KD. And if we know what the distribution coefficient KD is, then we have everything we need to do to be able to see what the retardation is. And if we know what the retardation is, then we can say how far the plume will go in a given time, how much it will be attenuated over the case where it's conservative, and what the concentrations will be as we go downstream. So that's where we are. Okay. All right, that's all I got for you today. Any questions?